Hey, what's up, guys? This is John here again. So today, let's take a look at this LeetCode problem, number 1145, binary tree coloring game. I think this is a very interesting tree problem. Okay, so the description of this problem is kind of long, but basically, just to summarize, what it is asking us to do is we have given like a binary tree. Okay, and a binary tree means that one node can only have up to have up to two child, right? Basically the left and the right. Okay, and initially and we have two players. So initially there's a first player that can color basically can color any numbers, color any number node, and the node is from 1 to n. And then after the first person coloring the first one node, and we as the second player will place will color a different node other than the already colored node here. And then every time one player can only color the another node that's next to the next to his color. So which means that at the first time, right? Let's say the first player one colored node 3 here, and we colored node 2. And on the next round, right? The uh, the person, right? So the first person can only color either six, seven, or one because only those three nodes are connected to three. Same thing for the two here. So that's how we continue coloring this this tree here. And we stop if either of the player can coloring any more can coloring any more nodes. And it asks us to check if there is a node that exists, right, for us to play, so that it's guaranteed that we can win the game. So to win the game, I mean basically after either either of the player can color a node, who color the most nodes will win the game. Okay, yeah. So that's the basic idea, and there's some constraints here. And let's say, for example, the n is odd, right? So the total nodes is odd. So why is that? So because as you guys can see, so when we will stop coloring? Basically, when all the nodes are colored to either one color or the other. And why is that? Because the regardless where at their initial starting point, right? In the end, since it will eventually basically can color all the neighbored nodes, right? And then so keep going until all the nodes have been colored. So that's why in total we'll have like n nodes colored. And since n is an odd number, that's why it's guaranteed that we can either have a true or false. There won't be a even color nodes for two players. So that's what this odd number means here. Okay, so now here the question is, how can we check? How can we check if we as a second player can win the game? So to do that, right, we have to analyze what is our best strategy to color a game, to color like the to color the next nodes, right? So if you watch it, if you think about it, right? So let's say the first player, right? So player one colored this node, assuming this node has like, one node in the tree can only has one branches, either a parent, right? Or a left child or a right child. So here it could be have different nodes here, right? Same thing for the right side, right? And same thing for the parent, right? So parent could have like other nodes here, right? So if the first person places a node here, our best strategy is always to place the it's always to place a node next to this one, either on the left side, on the right side, or on its parent side. Why is that? Because the moment we place a node here, basically we're blocking this entire branch, right, for this number. Because once we have placed it here, all the all the remaining nodes starting from here will be ours, because there's no way the player one can reach this side anymore, because we have blocked that path, right? Same thing for us when we cannot go to his way, because this path has been blocked by the first player. So now the question comes down to, right, since we have three options here, we can either place a node on as this one's left child, or right child, or its parent child. Sorry, or its parent. And all we need to do is we just need to check how many nodes, how many subnodes for this left subtree, for this right subtree, and how many nodes for the remaining parts, right? Starting from the parent and the remaining. So to get the total subnodes for left and right subtree, it's pretty straightforward, right? We just use a DFS to collect all the number of nodes to this left and right. And so for the parent node, for the parent size nodes, it's also kind of like straightforward, since we have n nodes, right? We already have n here. If n minus left total nodes, right, minus right total nodes, and then minus one, because we also need to subtract this one itself, and then this this number will become the parent nodes, right? The remaining nodes on the parent side. So we have a parent, we have a left, and then we have a right. So that's the three possible nodes we can get, right? So we just need to check among all those three numbers, we get the maximum out of the three numbers, and then we'll check out of the most color numbers we can get, if this max number is greater than half of the total nodes. If it's greater, then we know, okay, we can win the game. If it's not, then we know we cannot win the game. All right. Cool. So that's the intuition for this problem. All right, so let's start coding. So first thing first, we need to get the subnode, right, for the left child and the right child. So to do that, I'm going to create helper functions to count nodes. Okay, so I'm going to count nodes for the current here, and so to count the node is simply a DFS, right? And if not current, right, if we have reached the end, we simply return 0, right? Else we have a left equals to what? The count node current left, right? And then we have a right, we go to the right as well, and then current dot right, and then we simply return what? Left plus right plus 1. So plus 1 means that we're counting the current node as 1, and then we're accumulating the left side nodes and the right side nodes, right? And we do this by recursively going to the bottom, and then we calculate calculate all the nodes from bottom up. Okay. All right. So that's the helper functions to count the nodes for given like a node here. And now the next step is what we need to find this x here, because okay, so it says that the first player will place his node on this x node. So to find that, we just need to find x. How about that? So find x is also like a DFS, right? We also so for all these tree problems, DFS are like a common solution. So we just do a if not current, right? So if not current, we simply return, or we do this one. Basically, we just copy copy and paste here. But the only difference for this one is the whenever we find the x, we will start counting the nodes for its left child and the right child. That's why we're gonna have like a check here. So whenever the current node is the x, then we know, okay, we're going to count this node, right? And so to store those two values, I'm going to left nodes equals to the right nodes equals to the I'll just call it parent nodes equal to 0. So here, since we're going to set that, I'm going to non-local, right? Non-local left nodes and the right nodes here. So whenever we find the x here, we know, okay, so the left nodes will be what? Will be the count nodes right here. So I'm going to call this count nodes, and I'm going to pass in this current dot left, and this current nodes, the count nodes will give us the total nodes starting from the left child, right? Same thing for the right nodes here, right? So here we have a right, and then we simply return because we don't need. There's no need to moving forward. Okay, so and after this one, right? So and then here we do find x, of root. We're starting from root. We're trying to find the x, and while we're finding the x here, we'll also populate the left nodes and the right nodes. Okay, so since we have that, now we can also calculate the parent nodes, right? Like I said, parent nodes will be n minus left nodes minus right nodes and -1, right? Also subtract this x itself. So since we now we have all three numbers possible nodes we can get, which simply just need to do a max of left nodes, right? And then the right nodes, and then the parent nodes. If this one is greater than the n divided by 2. Yep, that's that. So among all these possible numbers, if any of them is greater than half of the numbers, then we just put that nodes on either on its parent as its left child, or on his right child. All right, run the code. All right, accepted, submit. Cool. All right. Yep, I think that's it, right? I mean, I think for the time and space complexity, it's just like at the end, right? Because we just simply, the worst case scenario, we just, not the worst case, we will anyway traverse all the nodes, so it's just O of n, right? So cool. Yeah, I think that's it. That's pretty much it is for this problem. It's still a DFS tree problem, but the tricky part for this one is that you have to find out what's what's we as the second player, what's our like best strategy. So our best strategy is always try to block one of the three branches of the first player. And then as long as you can figure out that part, I think the rest should be pretty straightforward. And then there you have it. Cool. All right, I'll stop here. Thank you so much for you guys to watch this video, and stay tuned. See you guys soon. Bye bye.